Hey, welcome back to the channel. So I get often asked, how do I read an oscilloscope? How do I use one? So I thought to myself, you know what, this would be a good time to do a video on the oscilloscope. So the one I'm going to show you here is just the one I happen to have. It's not one that I'm promoting. I'm not saying it's good or bad. It's just the one that I happen to have that I can use that's readily available to me. So with that being said, yeah, I'm going to do a video and I'm just going to show you the basics of an oscilloscope, because depending on the model you have, there could be a lot more features available. They could have their own little quirks. So I'm not going to get into, every single feature of my oscilloscope, because yours may be different. But as far as how you read a sine wave or any kind of waveform on your oscilloscope, that will be the same. So that's what I'm going to cover in this video. All right, so with that being said, let's get into the individual controls to start with. Okay, so here we are. I have, coming from my function generator, I'm putting out 20 volts at 60 hertz, and that is being shown on my sine wave. Now, I'm not going to get in right now how we read this. I want to get into how all these little buttons work on here and just the basics, more or less. I'm not going to get into every feature that I have, but just so you know where this sine wave is coming from, it is coming from my function generator that's putting out 20 volts at 60 hertz. Okay, so I'm plugged into channel 2. Notice on my oscilloscope I have 2 channels. Most oscilloscopes will have more than one channel. Some will have 3 or 4, I believe. Majority of them will be 2 channels. There's a channel 1 and we have a channel 2. I'm currently on channel 2. Notice it's kind of outlined with purple, right? That's nice, because when I look at my oscilloscope, I have a purple line. That tells me that I'm reading channel 2. I could have another probe in channel 1 and I could be reading a different part of the circuit. And what's nice is when I bring that wave up onto the screen, it will display as yellow. So let me show you. I'll just turn off channel 2. I'm going to switch my probe over to channel 1 and activate that one. Now, it's all over the place. Most oscilloscopes will have this feature. Now, I could either turn my volts per division and get this where I could see it, right? If I put it back, or I could just hit the auto trigger where it kind of analyzes what's coming in and sets it up for you. So now I have a nice, clean, stable sine wave. Notice how it's in yellow now. So I'm reading off of channel 1. And I'm not sure if you could see this, but it's showing me on this screen, I have a voltage peak to peak of 20.2 volts. And right now, where it says channel 1, 5 volts, that relates to my volts per division. Notice how it changes when I change the knob, when I rotate the knob left or right. So here, 10 volts per division. So what does that mean? I'm going to put it back to 5 volts per division. Per division means every full square, from top to bottom or bottom to the top, whatever you want to think of. When we look at this scale, when we're going up or down, that axis is for voltage. Left to right, that's how we read the time period of this sine wave. And we'll get into that soon. Right now, let's just look at the voltage. So to read voltage, we're measuring, or what we see here is a voltage peak to peak. And like I said, right now, our peak to peak voltage is 20.2. So from this very negative portion of the sine wave to the very top positive portion of the sine wave is 20.2 volts. Okay? And that's about right, because that's what I'm putting out from the function generator, 20 volts. Now to read this, if I'm on 5 volts per division again is per square. So I'm not sure if you can see this very well. I think you can. But notice the sine wave, how many squares it takes up. I count 4. So if I come to this peak here, this negative peak, and I start counting my divisions up, so 1, 2, 3, 4, which is where the top of the peak is, well, 4 times 5 is 20 volts. That's where you're getting 20 volts peak to peak. I'm getting 10 volts in one direction and 10 volts in the other direction. Okay, so that's kind of how you read the voltages. And again, you can change that. So if I turn my volts per division knob to the left, now I can see on the scale that each division is worth 10 volts. So now each square is worth 10 volts. Okay. There are subdivisions within each division. So those you would have to calculate what each tick represents. Because you might not be right at the line for a division. You could be somewhere in the middle. Right? So right now if I'm at 10 volts per division, well, there's 5 ticks per division. So if I just divide that by 5, I get 2. So that tells me that each little tick within the division is worth 0.2 volts. And that makes sense, because if I go 0.2, 0.4, 0.6, 0.8, and then I get 10, and then 10.2, 10.4, 10.6, 10.8, then I get 20. All right? Don't get confused what per division means. It's not the subticks. A division is the complete square. All right? One complete square. Okay, so that's how you read the voltage on an oscilloscope. Let's look now on how we read the frequency. Okay, so now to capture the time it takes to complete one sine wave, we can measure the divisions from left to right. So again, top to bottom, that's how you're measuring your voltage on the oscilloscope when you're looking at your divisions from left to right, or right to left, whatever way you want to look at it. You are measuring the time. So we can easily determine how long it takes for one complete sine wave to do a full 360 electrical degrees. Now, I'm going to show you something here. What we have are some positioning buttons as well. So I went over the volts per division button, which on mine is the bigger knob. There's also a positioning button for that. So I can move my sine wave up or down wherever I want. Now, why would I want to do that? Well, let's say that your sine wave, in this case, you're trying to determine voltage, but you want to maybe get this, maybe you want to use this point here as a reference. Well, for me, I don't want to use my reference point halfway through a division. So I may find it easier if I locate my sine wave, the reference point I want, at a starting point that starts basically at 0 at a division. And now I can easily count up. All right? So I like to use my positioning to get a good reference line when I need something, where I need a position to start counting my divisions from. I don't want to start halfway through the middle. All right? So whether that's the bottom or the top that you want to start at, all right, that's up to you. But that's what I use it for. I get it one of those two sides on a nice, line, not somewhere in the middle. And that's what I'm going to show you here for the frequency. So for here, I'm just going to put my volts per division back down the center. All right. Doesn't matter for what I want to do to capture how long it takes to do a complete sine wave. Now, I want to pick on my sine wave. Where do I want to start measuring to see how long it takes to do one complete cycle? All right. So I'm kind of off a bit here. It's up to you where you pick. I could start at the very peak. I could start at 0 degrees, 90 degrees, 180, 270, or 360. It doesn't matter as long as you're measuring one complete cycle. Okay. Now, right now, when you look at my oscilloscope settings, I'm set to 5 milliseconds per division. All right. Where's that set from? That was set from my horizontal. So now, when I went to the right, each division is now, from left to right, worth 2.5 milliseconds. And so on. Right? So all oscilloscopes somewhere on the screen will tell you what you're set for, right? Why would you want to change this? Well, one reason is if you had this, so right now I'm at 50 milliseconds per division, that's kind of hard to read, really hard to read. So you're going to want to spread it out so you can at least see a complete sine wave. So here I'm going to leave it at 5 milliseconds per division. Now, I can move this left to right, all right? And again, why would you want to do that? Well, say I'm trying to capture one full cycle. Well, I don't want to start halfway through my division. So I will move my sine wave, the beginning, my 0, to a 0, 0 point. That looks pretty good there. So I'm going to measure from 0, and I'm going to do one complete alteration back to 360. So from this point to this point. I'm set at 5 milliseconds per division. So if I look at this, I am 5, 10, 15 point, we'll say 1.5. So 15, we'll say 15.2. We'll just go up a bit. Yeah, because so where I'm getting that too, by the way, is if each division is worth 5 milliseconds and there's 5 ticks per division, subticks, then each of these subticks is worth 1, right? So again, I got 5, 10, 15, 16.5 milliseconds. So this sine wave right here, it takes 16.5 milliseconds to do one complete sine wave. So 0, 90, 180, 270, 360. To do one full cycle takes me 5, 10, 15, 16.5 milliseconds. Okay? Okay, so maybe you're asking, well, you said the frequency was 60 hertz. Well, it is, and you can actually see that right here. It's kind of fluctuating a bit. Here's a nice little feature too with oscilloscopes. You can actually lock it or you can stop it. Right now, it's continuously updating. But if you wanted to freeze your reading, you may have, like I do, a run stop. And if you hit, at least on mine, stop, it freezes it at that point. So even if there was a change in the circuit, I'm not going to see it because I'm no longer triggering. But we'll leave it like that right now. So right now, yeah, my frequency is basically 60 hertz. I had 5 milliseconds per division, right? So 5, 10, 15, 16, I'm going to call it 17. It's almost at that second line. Now remember, the formula for frequency is frequency equals 1 divided by time. Our time is 17 milliseconds. So if you take your calculator and you go 1 divided by decimal 0.17 for 17 milliseconds, I get basically 59 hertz, which is basically what we have. So yes, in 1 second, I have 60 hertz because hertz is measured in seconds. What I'm looking at here is one cycle, right? Which is going to happen in milliseconds. If an entire 60 hertz cycle happens in a second. Okay, so again, I just verified, yeah, that makes sense. If I measured 17 milliseconds and I went 1 divided by 17 milliseconds, it comes to 59 hertz. So that is correct. I can start this back up. It's re-triggering. It's going to just fluctuate a bit. But that's that. So again, we got 2 channels. I can adjust the volts per division, which is your peak to peak. I can move that up and down if I want to get a different reference point. And I also have left to right my frequency, or not my frequency, the time period. Let's not get the 2 terms messed up. We have 60 hertz, that's our frequency, but we're looking at a period of time, right? So right now, 1 period From 0 to 360, I'm set for 2.5 milliseconds. Each division is 2.5 milliseconds. Okay? And I can move that back and forth just in case, maybe I wanted to calculate this one. Right here at 0, I'm not right at a nice 0, 0 reference point. I'm kind of 3/4 through one of my divisions. So if I just line that up so that my 0 degrees is at a crosshair, we'll say. Now I just count my divisions for one complete cycle. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 divisions times 2.5. 22.5 milliseconds. Now if I take 1 divided by that, 1 divided by 22, 1 divided by decimal 0.225, that math doesn't work out. So I probably got my count off because I'm only getting like 45 hertz and we're pushing out 60. Okay, so let's see where we went wrong here. If we are 2.5 milliseconds per division, I have 1, 2, 3, 4, 5, 6. 6 divisions. We'll say 6.1, 2, 3. Let's try that one. 6.3. 6.3 times 2.5 equals 15.75. 1 divided by decimal 0.1575 gets me 62 hertz. Right, so it's always good to double check your work. My mistake was I counted my submarks as a division in this case, and it should have been like a decimal number. So again, 2.5 milliseconds. So 1, 2, 3, 4, 5, 6 point, we'll say 246, 6.6 times the 2.5. All right, that would be our period. Okay, and again, frequency equals 1 divided by a period. Okay. Anyways, that's it in a nutshell. There's a lot of features on here. The best way to learn these is just to play with them, right? But these are your main components here. One thing I should mention too, I'm measuring AC, so I should be sure to have, actually this should be on AC. I'm measuring AC, it doesn't change it much. But you'll notice there's a lot of other parameters that you'll need to set depending on your circuit. Okay, so here I have AC coupling, volts per division. So if you look at a probe, you'll notice there is a little selector switch. I'm going to disconnect my probe and show you, just so you can see what it shows here, or what I'm talking about. So I have my probe, if I can get off here. Okay, I have my probe. Basically, I got a little hook piece here. See that all right? Try to get the contrast. A hook piece I can grab onto something, or you can take the end off, and now you can just probe it with a little point. Okay. I like to clip onto stuff, so I put that attachment on, and it's spring loaded. You also have the ground lead that's attached to it. Okay. But what you'll also notice too is you have a selector switch. Okay. On mine, you won't be able to see it because it's embossed in the plastic, but it's set to 1 time. Right? So whatever it's reading, that's what it is. But say it was so small, the measurement was so small, you couldn't read it. So what you can do is you can change your switch to be times 10, and it will multiply your value times 10. You can also do it, at least on mine, in this probe section. And you can see I can go times 2, times 5, times 10, times 20, all that good stuff there. Right? So if you're getting some really weird measurements that don't make sense, you might have it so that your probe setting is off. And let me show you for example. I'm going to hook this back up to the function generator. I know you can't see it, but it's here. So if I hook this back up to the function generator, well, don't have my ground on, so it's pretty noisy. There we go. And I were to go back in here and change the probe setting, watch what happens to the sine wave. Let's go times 20. Well, that didn't work because nothing happened. All right. Okay, so if I go into my oscilloscope, look at the voltage, I'm still pushing out 20 volts, peak to peak. Okay, my RMS is 7 volts, meaning from 0 degrees up to here is about 7 volts, not the full 10. Okay, but look what happens when I change my probe setting. If I change my probe setting to, say, times 10, and I hit enter, why don't you have to hit enter? Look what happened to my voltage peak to peak. It's multiplied it by 10. It's telling me that it's 206 volts. So if you're working with these oscilloscopes and you know that this is not right, I'm only putting out 20 volts, but I'm showing 204 on my oscilloscope, guarantee you your probe setting is wrong, right? So that's the first thing you want to check. If you can't figure anything out, all oscilloscopes will have this default setup. If you hit default setup, it basically just wipes everything back to default. And then if you hit the auto, it reconfigures it and puts it back to a nice readable scale. Now I'm going to switch the probe on my setting on the probe itself. Look what happened. So I put it to times 10. All right, so now it's only showing 2.2 volts. Okay, so let's talk about sine waves. So right now we have a sinusoidal wave. We got a starting point of 0 degrees, right? So this would be just like what comes out of your home receptacle. So we got a positive peak, and then we transition back down to 0, and then we go to the negative alteration. We have a negative peak and back to 0, right? So that's one alteration. But yeah, you have a sine wave. I'll show you some other ones here. We have, change this up. There is your square wave. Now on here, why it looks like that, not sure, because it's not really a square. I'm kind of leaning off a bit here, but it's not a nice smooth sine wave. That'd be considered a square wave. Same voltage, all right. Pulsing, which I can't. So here's a triangle wave. Looks like a sawtooth. All right. So that's a triangle wave. And again, this is all coming from my function generator. This one is a partial sine. A CMOS. I don't even know what the CMOS is for. Here's obviously a DC. All right. DC is direct, like just it's on. It doesn't alternate like AC. Okay. There's a full wave, half wave. All right, so all these sine waves I can use out of my function generator I have. But yeah, as you can see, the oscilloscope can capture any type of waveform. So it makes it handy that way. But other than that, you still read it the same. Okay, so next I'm going to show you the actual coming off of a plug. So 120 volt, 60 hertz. Okay, so I don't recommend you do this at all. I have my probe stuck onto the receptacle. Here, I'll show you what I have. Basically stuck on to the 120 volt portion of the receptacle. Again, I don't recommend you do this. I'm doing this for demonstration purposes. Okay. All right. So that's on there. I'm measuring right from the receptacle. Let's see if this makes sense with what I've told you. So right at the bat, notice my values. I've added volts RMS, volts max, volts peak to peak, and notice they're at 12.4, 17.2, and 34.8. Well, obviously we have more than that coming out of a receptacle. What I had to do was put my probe selector switch to times 10 because my oscilloscope couldn't read that high of a voltage. So I had to kind of shrink it down. Now that selector on my actual probe is times 10, I'm going to come in to here on my probe and multiply those values by 10 on here. So if I do that, turn this back on, now look what we have. I have 124 volts RMS. I have 172 volts max, meaning peak to peak. Well, peak, sorry, no, from 0 to my top half. So either way, so from 0 to the positive peak is 172 volts, or 0, or in this case we could say 180 to 270 electrical degrees is 172 volts. Peak to peak, so from peak positive to peak negative, 348 volts is what we have out of your standard receptacle. Now, why do we not read 172 volts when we, connect our fluke meter? We're out on a service call, or we got our meter plugged into our wall outlet. We're only seeing 120 volts. Well, our meters only read RMS values. They don't read the peak to peak, or even the peak voltage. And again, notice my RMS value is 124 volts. It's a little high on my end. But yeah, you'll see anywhere from 115 to 124. Usually it's averaging about 120. So we say 120 volt outlet. But just remember, just because you plugged in your meter and that's what you're seeing, you actually have, coming out of that receptacle, 172 volts max. Okay? And remember, you could take your multimeter reading, which is measuring RMS, and you can calculate on your own what the peak voltage is. You just take your RMS value times 1.414, and that will give you peak. Okay? So, but just remember that. So if somebody, tells you that, the maximum voltage at a receptacle is 120 volts, well, it's not. That's just what your meter reads, because it's reading RMS values. It's not reading the voltage max. Okay, but yeah, there's your sine wave coming out of a receptacle outlet. And yeah, I hope you like this video. Again, the only way to really learn your oscilloscope is just to play with it. Read the manuals, just play around with it, and they can do quite a bit, and they're pretty handy. As an electrician, I have used one out in the field once. I used it to figure out why an encoder kept blowing out every time a motor energized. And even though our cables were shielded and separated, somehow the motor leads, 600 volt motor leads, were inducing a voltage peak of in the hundreds of volts to a 24 volt device, and it was blowing out the circuitry. But you're not going to read that using your multimeter, right? We had to use an oscilloscope to capture that voltage spike. So they are handy to use, and again, it just takes practice. So I hope this video is somewhat helpful, and I hope it gives you just a baseline on what all these knobs do and how you read the sine wave. Again, you'll just have to practice, but when you do that, you start to see how it works, and it actually is a very simple meter to use. All right, so hope you liked it, and subscribe, share the channel, and I have another one coming out soon that is on the updated voltage drop calculation method. All right, so that's going to be coming out very soon. Watch for that one. It's going to be brand new because they've totally changed how D3 looks in the Canadian Electrical Code. All right, have a good day.